possess a characteristic not only magnitude like scalars, but also directions, orientations. So scalar does not have orientations. Energy does not have orientations. Temperature, there is no orientations. But some quantities beside the magnitude require also the notions of directions. For instance, force, velocity, displacement, accelerations. These are the quantities which possess not only magnitude but also directions. So this kind of quantities is best described by the use of vectors. Okay, and then you have learned the vectors during your first year. So we did a brief review on some basic algebra of vectors. We specifically looking at dot product and also scalar product of two vectors. Okay. So the dot product of vectors give two vectors give you a scalar. Cross product of two vectors give you another vector. And then we have also seen change of basis. So from one coordinate system to another coordinate systems in the way how we represent a vector, because a vector can be described by many ways, depending on the coordinate systems that we are working, depending on the basis that we are working. So the component of the vector will be different if we use different coordinate system. Okay, and then we have learned how to express the components of the same vectors using two different coordinate systems, two different bases through change of basis. And then we have seen a few examples on that last time. And then also we have discussed briefly about invariants of the vectors. So invariants are quantity which are not affected by the change of coordinate systems. The component of the vectors we have seen depend on the choice of coordinate systems. That is why we can always change the component from one coordinate systems to another coordinate systems. If we choose different coordinate systems, we end up with different components of the same vector. And then if the components depend on the choice of the coordinate systems, if the components depend on the choice of the axis, what is the characteristic of vector which will not change with the change of the coordinate systems? And this is called as invariant, we have seen. Example of invariance of the vector is the length or the magnitude of the vector. So regardless of the choice of the basis, the length of the vector must remain the same. Either you express the vector with one coordinate systems or another coordinate systems. If you check the length, it must be the same. So it is not affected by the choice of coordinate systems. And this characteristic is called as invariant of a vector. Characteristic which will not change with the change of the coordinate systems. So these are the things that we have discussed. Scalar and then vectors. Can you see my slide moving?
Yes, okay.
All right. Okay. Now I move to tensors. So we started by some quantity can be described by a scalar like energy, temperature, and mass. Some quantities can be described by a vector. For instance, force, as I mentioned, accelerations, velocity, displacement. Some quantities require other way how to express it. Okay. So in physics and mechanics, besides scalar and vectors, we have also what we call as tensors. So tensors are basically geometric entities introduced into physics or mechanics to extend the notions of scalars and vectors to higher orders. So this is the extensions of scalar, the extensions of vectors. What are the quantities which cannot be described by scalar or vectors? Stress. You will see, mechanical engineer, when we deal with the stress, it must be described by a quantity other than scalar or vectors. Strain also the same. Elasticity tensors also the same. So these are the example of the quantities, mechanical quantities that we will use extensively in this lecture, and these are the quantity that can be described by tensors. Okay, so how we give notation to tensors? If a scalar is just simple, for instance, letter, you can use letter. When vector, we represent it by a letter, and then you have arrow above it. Here in this lecture, I will use this notation for tensors, for tensors. So for instance, the stress tensors, this is the stress notations, and then we have two lines below it. I have strain here, two line below. I have F, two line. I have A, three line. I have E, four lines. What does it mean? So the number of line below the notations represent the order of the tensors. So sigma, epsilon, and F are second order tensors. A here is example with three line below is third order tensors. E is notation given with four line to fourth order tensors. Okay. So here, stress and strain that we are going to use extensively are basically second order tensors. Okay. Elasticity tensors, I will not talk much about it, is the example of fourth order tensors. So how many components of second order tensors? It's actually easy. It is by the formula of 3 to the power of order. Scalar is basically tensor of order 0. So the number of component of scalar is 3 to the power of 0. It is 1. So there is only one component of scalar because it has not any direction. It does not have any directions. What about vectors that we learned before? It is first order tensor. So the number of component of a vector is 3 to the power of 1, first order. So there are 3. Second order tensors possess 3 to the power of 2. So a second order tensor possess 9 components, and so on and so forth. The third order tensor possess 3 to the power of 3 equal to 27 components. And fourth order tensor is 3 to the power of 4, which is 81 components. So elasticity tensor possess 81 components. Okay, so this is the tensors which is introduced in physics and mechanics to describe certain quantities which will be needed for analysis. Okay. So since we are mechanical engineer, work mostly with stress and strain, obviously we will focus only on second order tensors. And second order tensors can be imagined, can be pictured by a matrix of 3, 3. For instance, this is A is a second order tensors, and the component is given by A11, 1, 2, 1, 3. 1 means the first index means this is the row, and then the second one is representing the column. So A12 is put in the row number 1, column number 2. Row number 1, column number 3 for A13, and so on and so forth. So these are how we can imagine, how we can picture a second order tensors which possess 9 components. Again, second order tensor component is 3 to the power of 2. So it is 9. As you can count here, there are 9 components of the second order tensor. So stress and strains are the example of a quantity which can be described by second order tensor. Okay. So again, I have to highlight that the third and fourth order tensors are important in Mathieu's modeling. But in this lecture, we are going to focus only on second order tensors, which means that we are only looking at the stress and strain tensors here, okay, which we can imagine as a matrix 3, 3. Again, if you have any questions, you can always interrupt me here, ask the questions here directly, or you can type in the chat box, okay? All right. So now, let's have a look on more precisely to the components of a second order tensor. So when we talk about tensors, again, here we focus only on second order tensor. Okay. So this is how I write. This is a tensor A. Two lines here correspond to the fact that it is a second order. And then we can represent it by a matrix 3, 3. So these are the components of the tensor A. There are 9 components. Okay. If we look at closely to the components located along diagonal. So this component A11, A22, and A33 are located along diagonals. And these components are called as normal components. Okay. And then we can see also some of the components are located outside diagonal or called off-diagonal components. So these are a component which commonly called as shear components of tensor A. So you can imagine stress and strain are example of second-order tensor. So if we write here A represent the stress, then the normal stresses are put here. And the shear stresses are located outside the diagonal. That's how we put it in the matrix 3, 3, the stress state in the materials, the strain state in the materials by the use of second-order tensor. Is that clear so far? Yeah?
Yes, doctor.
Okay. I will try to go slowly. Bear with me if it is too slow because I need to make sure that you follow the basic principle. Okay. Now, what are the mathematical operations that we can use for second-order tensors? In vectors, when we deal with vectors, we learn about dot product and cross product. If we have two vectors, the dot product of two vectors give you a scalar. Okay. The cross product of two vectors give you another vector. Right? So here, for tensors, I will just discuss about two mathematical operations that will be useful for our purpose later, which is trace and double contractions. What is trace of a tensor? What is double contractions of two tensors? So here, for instance, I have two second-order tensors, tensor A and tensor B. The components are given there. Okay. So if I want to evaluate the trace of tensor A, what does it mean? The trace of tensor A is defined by the sum of the diagonal components, the normal components. So trace A is defined by A11 plus A22 plus A33. This is definitions. Okay. If it is trace of the tensor B, it means that it is B11 plus B22 plus B33. We look at the normal components only and we sum up. Okay. The second operation is called as double contractions. So it is typically noted as the two dot here. So A 2 dot B here, which means that A double contractions to B is basically equal to the trace of the product between A transpose times B. This is the multiplication, the usual multiplications of two matrices, okay, which is also equal to the trace of B transpose A equal to AB transpose, and so on and so forth here, equal to B double contraction A. So which means that the double contractions is commutative. So A double contraction B equal to B double contraction A, where the T here is again is the matrix, means it's the transpose of the matrix. So AT means that you need to transpose the matrix A and then you multiply matrix B and then you take the multiplications of the two, take the normal components, the sum of the normal components of the two products. Okay, so this is the definitions of the trace and double contractions that used in second-order tensors. Two notes here. A trace of a second-order tensor gives you a scalar. Obviously, here you can see the trace of A is simply the sum of all diagonal components, all normal components, and it will give you a scalar. Double contractions of two second-order tensors give you also a scalar, because you will see you have here the product of inside the bracket will be another matrix, but when you take trace of that matrix, then you end up with the above here, which is a scalar. So double contractions of two tensors is more or less analogy to dot product of two vectors that we have learned. So dot product of two vectors give you a scalar. Double contractions of two second-order tensors give you a scalar. All right? I hope that is clear. This is two basic mathematical operations that we can do for second-order tensors. Okay. So now, in vectors, we have learned about change of basis or change coordinate systems. This is dealing with the fact that the value of the component of a vector will change depending on the choice of your coordinate systems. If you choose two different coordinate systems to represent the same vectors, you have seen that it will give you two different value of components. It is still the same vector. The components are different simply because we express it to two different coordinate systems. And we have learned how to change from one coordinate system to another coordinate system through the use of change of basis principle. How about a tensors? We can do exactly similar things. Components of a tensors, the value depend on the choice of axis. For instance here, if I have a tensor A, the value of components, 9 components, are given here with respect to these coordinate systems, E1, E2, E3, for instance. But if I express the same tensor using another coordinate system, using another basis, for instance, E1 prime, E2 prime, E3 prime, then I will have new set of components. A11 prime will be different from A11. A12 prime will be different from A12. So this will be different. It represents exactly the same tensor, but the components are different simply because you express with respect to two different coordinate systems. Exactly similar like in vector. Okay. Now, how can I determine, for instance, if this is the old components and this is the new component, how can I relate between the new component to the old components? Change of basis, like what we did in vectors. Look back in vectors, okay? So we have another equations which link between the component of old tensor to the component of the new tensors here. The new component of the tensor, sorry. So I have to clarify to make sure that there is no mistake. We describe one tensor using a number of ways depending on the coordinate systems. The components of this tensor will depend on the choice of axis. Let's say if I call this is E1, E2, E3 as an old axis, then the component with respect to the old axis are given here. If I express with respect to the new axis, another axis here, then the component of my tensor A will be this one. So now, how to link between the components of the new components of tensor A to the old components of tensor A? Then I represent it in this way. The new component of A is simply, if I put in the matrix, it is the transformations matrix you transpose times A times Q. So where Q is exactly the same like what we learned in vectors. As simple as that. Okay. So we can get the new components of a tensor A from the informations of the old components. All right. Okay. Exactly the same with slightly different equations because it involves second-order tensor. Okay, now I will stop in this example for 10 minutes, give you a chance, okay? Uh, this is an example of how to use double contractions and trace, okay, for second order tensors. So here are the questions. Give the expressions of the strain energy density W of an isotropic linear elastic materials if the strain energy density is defined by half of the contractions between the stress and the strain tensor. So W is defined by half of the contraction between stress and strain tensors. Okay. Note that both tensors are symmetric, means that here the shear component 1, 2 equal to this one, 1, 3 equal to this one, 2, 3 equal to this one. So there is a mirror, symmetric the components. Okay. Similarly for the strain here. So epsilon 2, 1 is equal to 1, 2. Okay. All right, and so on. So there is no number here. It is just a symbol. So in the functions of sigma 1, 1, sigma 1, 2, and so on, there is no number here. Okay. So the question is, give expressions. If W is half of double contractions of matrix sigma to matrix epsilon, like this, what will be the result? And then what will be the unit of W? So I will give you 10 minutes from now. So it is 11:30. So I will come back to discuss at 11:40. Okay, quickly. So how many of you managed to understand the questions and get the answer?
I understand the question, but need some time to need to.
Okay, great. So please go ahead. We will discuss again in another 2 minutes. Yeah. Okay, let's have a look how we do this one. So basically here we need to do the double contractions between the stress tensor and the strain tensor. So you have the equations given there and then the definitions of double contractions. Noting that both stress and strain tensors are symmetric, so it is easier. Okay, so how to do this? Okay, just now I think Hadi mentions that it is a bit long. It is true. So we need to strategize how to make it slightly shorter. Okay, instead of doing long calculations. So what can we do? Let's have a look in the next slide here. So this is the two tensors. Again, both are symmetric. Okay, and then this is the definitions of double contractions. So W is half of double contraction sigma epsilon. And then this is by definitions equal to sigma epsilon product, and then you get the trace of the two product. Why there is no transpose? There is no need for transpose because it is symmetric. So sigma transpose is simply equal to sigma, or epsilon transpose is simply equal to epsilon. So no need for that. So if you look at here, what you need is that simply the sum of the final product between sigma and epsilon. So you don't need to do all the multiplications that will not be necessary. So if you look at carefully here, half remain here. Trace is the sum of the diagonal of these two products. So which means that I will just need the components of the product long 1, 1, long 2, 2, and long 3, 3. That is to make it easier. So you don't need to do all calculations. Slightly longer, it's fine, but it's slightly longer. Okay. So how to do that? And then we know that here, the tensor, the product, and the component 1, 1 is simply this one. If you look at the multiplications, okay. And then the component 2, 2 of the product sigma epsilon is this one. And the component 3, 3 of the product sigma epsilon is this one. So I can simply just sum up. So the elastic strain energy is simply given by the sum of the three, and then I can put in this way. Is there any question so far? You can do a complete multiplication between sigma and epsilon first. It's fine. To get another matrix, it's fine. And then you sum up the diagonal, it's fine. It will be also correct if you do it properly. It will take longer time because you do operations which is not necessary to get the information that we need. Yeah. Is that clear so far? Let me know, please.
Yes, sir.
Okay, yeah. It's a simple mathematical manipulations. All right, now, next question is, what is the unit of W? What do you think the unit? You understand what I mean by unit, yeah? Is it kilogram? Is it meter? Is it joule? What do you think the unit of W?
Is it Pascal?
Can you type, please?
Okay, sir.
Okay, if you have opinions, can you please type so I can have a look? I can see. Okay, Pascal. Andre, you mentioned that Newton per meter square, which is also Pascal. Okay, good. Others, Pascal also. Why do you think it is Pascal? Because it is multiplication between stress and strain. Stress is Pascal and strain is
Unitless.
without unit, right? Okay. But it is an energy. How come energy unit is Pascal? What do you think? Let's have a look to make things easier. Okay. Next slide here. All right. So the W that we have is for very general case. To make things easier, let's specify on the simple case that we can imagine easier when, let's say, if we deal with material subjected to uniaxial tensile load. So you have tensile specimen, and then it is pulled along these directions. Okay. So in this special case of uniaxial tensile load, the W reduces to become this one. Okay. Why? Because all other stress components are zero. Only sigma 11, which is non-zero, and epsilon 11 is the one that we have here. Okay, is that clear? Yeah. For the special case of uniaxial tensile load, only sigma 11 non-zero, sigma 220 vanish, sigma 330 vanish, all zero stress zero vanish, vanish, vanish. So you only have this quantity. So you mentioned that the stress unit is Pascal, epsilon unit is no unit. So you said it is Pascal. But it is an energy. What does it mean here? Actually, it is this one. It is area under the stress strain curve. Correct? It is an energy. But why the unit is Pascal? Nurul Atira mentioned it should be joule because it is energy. Which one is correct? Do you think? Arune and then Andre and Rais, you still think it is Pascal or it is Joule, or what do you think?
If it's energy, then I think it should be Joule.
If it's energy, then it should be Joule. But where it is, how come it is Joule while here the unit of stress is Pascal?
Not sure.
If we look at the unit here, you're right, it is Pascal. But it is an energy. How come energy has a unit of Pascal? Pascal is usually for pressure, for stress, but not for energy. And the area under stress strain curve is the energy density, elastic energy density. Okay, so how to deal with that? Okay, so you just need to have a simple analysis with the unit of Pascal that you're dealing. Okay, so you realize that actually here Pascal is Newton per meter square. And then it is equivalent with Newton meter per meter cube. Newton meter is joule. Okay, so it is joule per meter cube. We do not call it Pascal, even though it is equivalent, but we call it instead joule per meter cube. It is energy per unit of volume. That is why it is called as energy density. So the stress strain curve gives you information on the energy per unit of volume needed to deform the materials. The real amount of energy depends on the volume of your materials. The larger the volume, the higher the energy needed. Is that clear?
Yes.
Yes, yes.
So Pascal is okay, but we do not use Pascal. Okay? We use, because it is energy, we use joule per meter cube. All right. Okay. So just few remarks now to continue is that to summarize things that I have mentioned before, the magnitude of tensor components depends on the choice of axis. Exactly similar. You can compare it with vectors. And then similarly like a vectors, there will be a quantity belonging to a tensor which will not be dependent on the choice of axis, or it will be independent of the choice of axis. And this quantity is called also as invariant. For a vector, example of invariant is length, I have mentioned. Okay. Here for second order tensor, for the purpose of our materials modeling, okay, there are three most widely used invariants of the tensors. Okay, these three invariants is independent of the choice of the axis. Later we will go in more detail when we learn about hyperelastic materials. So the first invariance is the trace of tensor A. So the sum of diagonal components. If you take the sum of diagonal components, it will remain the same. Either you express, for instance, with the old components or with new components, the sum of the three normal components will always be the same. Okay, this is invariant code. And then the second invariant is defined by this one. Okay, you can check that this is also independent of the choice of the axis. And then if you investigate the value of determinants of the tensor, it will also be the same. If you express with old coordinate system, you have the set of components, take the determinants, you get one value. If you express using another coordinate systems, you will have another set of components, but when you calculate the determinants, it will be the same as when we use the old coordinate systems. So this is third invariant. So the determinants will always be the same. Okay, so this is again analogy to the length of a vector, where the length is independent of the choice of the axis. The component may change, but the length remains the same. In the tensor, the component may change, but the trace remains the same. The second invariance, the formula that you have there remains the same, and the determinants of the tensor will also remain the same. All right, so this is a closing remark for the second order tensors. All right, now here I have finished for the first part of lecture 1 regarding recall on the vectors and tensors. Now I will specifically discuss about stress and strain tensors in the following slide. Okay, so quickly here to recap what is stress. So I recall the definitions of the stress. It is the measure of average amount of force exerted per unit area of a surface. So you can simply speaking that it is the intensity of internal force. If we look at how the force act, the directions of the force with respect to the surface, so you have normal stress, you have learned normal stress where the force is perpendicular to the surface. If the force is parallel to the surface, then you call it as shear stress. And the unit of stress is Newton per meter square or Pascal or megapascal. That's the typical value that we use. Okay, stress is force per area. So you have learned about normal stress and shear stress. For normal stress, for instance, here, if you have cylindrical bar subjected to axial load, tensile in this case, and then if you can imagine that we cut in the middle here, then there will be intensity of internal force. This is called as the stress, and it is given by the axial load applied over the cross sections. This is the normal stress. Okay, because of the direction is pull, so the normal stress is tensile in nature. If it is push, then it is compressions in nature. Okay. And then we can also have shear stress. An example of shear stress is that if you have block here arranged in this way and then subjected to the load along this direction, load F. Okay. If we take out these sections and look at this area, then this area is subjected to the shear force, distributed shear force. The shear force is parallel to the area, and this shear force will generate shear stress here. Okay, and then it is given by here the shear force over the cross section. So you have learned also about this one. How about the strain? Okay, if the stress is the intensity of internal force, the strain is simply a measure of the shape change. How much actually the geometry of a material change because of the applications of the load. Okay, so this shape change basically relate between the geometry of materials before and after the applications of mechanical loading. So you have learned also normal strain. This is due to the actions of normal stress. Shear strain due to the actions of shear stress. So normal strain is defined by the change of length over initial length, while shear strain is simply corresponding to the angular change at some point in shape. So it relates to rotations. Okay? And strain is, as you have mentioned, unitless. So this is an example how the normal and shear strain is computed. So if you have, for instance, here bar, cylindrical bar with the initial length of L, fixed in one end, and then pull another end by force P, so that its length extended increases by delta. So this normal strain is simply delta over L. Okay. The shear strain is, if you imagine that you have this box here, cube, okay, and then it is shear along this direction, so that the vertical line here will incline to become this one, and then the angle which is initially perpendicular becoming theta here. So the shear strain is defined by, here is delta x, the amount of displacement here, over the length here, which is L. So it is related to the angle change of the angle. Okay, this is the shear strain. Now, how we describe the stress state in the real components. Okay. I take example the wing of an aircraft. So you know that during the service, the wing of aircraft can flex, okay, from its natural positions, depending on various aspects, the load, velocity, and so on. Okay, so let's say that I want to investigate the stress state in one point located on the wing. For instance, this one, I call it point Q, for instance. Okay, how to describe the stress state in this point? All right, now bear in your mind that a stress is a second order tensor. It can be described by the usage of matrix 3-3. It has 9 components. Okay, so here what we need to do is that, like a vector, we need to assign coordinate system. For instance, I can use x, y, z coordinate systems. And then to describe the stress state at point Q, I can draw an imaginary cube elements surrounding the point Q. And then the stress will act on that element Q this way, for instance. So in each surface surrounding point Q, you will have normal components of stress and shear components of the stress. For instance, here on the top, you have one normal stress and you can have 2 shear stress. In each side, in each face, you have one normal components, 2 shear components. Okay, so this is the stress state if we express it with respect to x, y, z. So you have sigma y, sigma x, sigma z, and tau xy, xz, and so on and so forth. As you can see here, probably it is too small, okay, in the screen, but there is an index given to each of the stress, depending on whether it is normal stress or shear stress, okay? As I mentioned before, we have a number of choice. This stress state is described with respect to x, y, z coordinate systems. What if I use another coordinate system? For instance, x prime, y prime, and z prime. Again, I draw imaginary cube element according to the new axis, and then I have new 6 surfaces here, and in this new 6 surface here, I have other stress components, normal and shear components. Okay. So as you can see here, you have different way, unlimited way of how to describe the stress state. The value of the components will be different depending on the choice of the axis. If you use x, y, z, then these are the components. If you use another axis, then this is the component, which will be different from the first one. Okay? So here, if I put all the stress here in the compact form of matrix 3, then I put sigma xx here because I use xyz coordinate systems, tau xy, tau xz, yx, and so on and so forth here. Okay, so the normal components are located here, the shear components are located there. And this is with respect to the old coordinate system, which is x, y, z. If I choose another coordinate system, for instance, x prime, y prime, and z prime, then my component will be given here, which are different from the first component there. Okay. So how to link between this to this one? It is through stress transformations, change of basis. When you learn in mechanics of materials, you know how to do stress transformations. So you look at certain angle and so on and so forth. Here, we use more the transformations, change of basis, using equation that I have mentioned before. Okay? So this is how we do it. Now, the next thing is that let's have a look more detail on the stress and strain tensors. We have said that those components located along diagonal are called normal components. So these sigma xx, sigma yy, sigma zz are normal stresses. Epsilon xx, epsilon yy, epsilon zz are normal strains. Okay, and then the rest located outside diagonals are shear components. If it is stress, then these are the shear stress. If it is strain, then these are the shear strain. This is the shear strain. Okay, so noting that stress tensor and strain tensor are symmetrical. Okay, which means that tau xy equal to tau yx, tau xz equal to tau zx, and so on and so forth here. So in summary, the matrix contains 9 components. But since this is symmetrical, it means that you only have 6 independent components. If it is stress tensor, you only have 3 normal stresses and you have 3 normal strains. So there are 6 independent components. Why only 6 instead of 9? Because the matrix is symmetric. So 3 normal components and 3 shear components. So you will have 3 again normal stresses, 3 normal shear stresses. You will have 3 normal strains. You will have 3 shear strains. All right. I hope that is clear. Is there any question so far? So this
for every for every stress and strain tenses, was it the same? I mean, like it always be the what do we call that? Symmetrical tenses.
Yes, correct.
Okay,
So
okay.
regarding what coordinate system you are choosing, it will always be symmetrical. Either you use x, y, z, or you use x prime, y prime, z prime. it will always be symmetrical.
Okay, so thank you.
Okay, any other questions so far? So again, which means that you only have 6 components of stresses. 3 normal stress, 3 shear stress. You only have 6 components of strain. 3 normal strains, 3 shear strain. For instance, here, the 3 normal stresses are normal stress along X, normal stress along Y, normal stress along Z, shear stress on the plane XY, which is this one, shear stress along the plane XZ equal to the plane ZX, and shear stress along the plane YZ equal to ZY. Okay, so this is how we see it. So we put all stress component in the compact notations of matrix 3-3. Okay, now few remarks here. Again, I repeat, the stress or strain state at a point can be described in a number of ways, which means that the components will be different depending on the choice of axis, okay, coordinate system. Consequently, the magnitude of normal and shear component will change according to the chosen orientations. Obviously, if I choose with respect to certain coordinate systems, I will have the 6 components of stress or strain. If I choose to express it with respect to other coordinate systems, I will have other 6 components of stress or other 6 components of strain. These 6 components will be different from the first one because you choose different axis. Okay, so now since you can always change the axis, then there will be special case like this in the third, which will be clearer in the next slide. Okay, you can find that there is a certain axis where the stress tensor or the strain tensor do not have shear component. And this axis or these directions are called as principal direction. Since there is no normal shear components, the normal component that you obtain when you express it with respect to the principal directions are called principal stress if you deal with stress, or principal strain if you deal with strain. So that's what happened. Let's have a look. Let's focus, for instance, now on the strain, but it applies exactly the same for the stress because they are basically the same matrix, okay, represented by the same mathematical quantities, which is matrix 3-3. So here is the strain, the components expressed with respect to XYZ coordinate system. XYZ are perpendicular to each other. We call it as 3 mutually perpendicular directions. I can choose to express it with respect to other coordinate systems, then I will have other components. And then from all the choice of possible coordinate systems, there is one particular coordinate system in which if I do the transformations to this new coordinate system, for instance, I call it N1, N2, N3, I have this particular shape of the matrix, which means that if we look at here, I only have components along diagonal, but not along shear components. So if I express the strain state using XYZ coordinate systems, I have both normal strains and shear strains. But if I express the same strain state, but with respect to N1, N2, and N3, I only have component non-zero along diagonal. This is very particular situations, okay? So these axis N1, N2, N3 are called principal directions of the strain. And the 3 diagonals value that we have here is simply called principal strains. If you are dealing with stress, then these are principal stress, and these are the principal directions of the stress, the same way. Okay, so how do we get this lambda 1, lambda 2, lambda 3, N1, N2, N3? Well, I will not go too much into the detail. You can recall what you learned in calculus, engineering mathematics, about eigenvalue problem. So we look at this. So I will not again go into so much into the detail of this one, but in order for us to get lambda 1, lambda 2, lambda 3, the three principal strains, then we need to solve from these equations the determinants of the matrix epsilon minus lambda I equal to 0. What is I? I is identity tensor or identity matrix, which is the value given here 1, 1, 1. Okay, so it is a simple and convenient way to get principal strains or principal stress. So whatever apply to the strain here, the strain matrix, apply exactly the same for the stress matrix. Okay, so the value of the three principal strains or stress can be simply obtained by solving that the determinants of this matrix, epsilon xx minus lambda, epsilon xy, epsilon xz, this one, equal to 0. So what happened is that when you set determinant equal to 0 of these terms, you will lead to polynomial equations of order 3. Okay, and then with this polynomial equation of order 3, you will have 3 roots. And the 3 roots that you obtain are lambda 1, lambda 2, and lambda 3. These are the 3 principal strains. These are the 3 principal stress if you deal with stress tensors. Any questions so far? I will stop here. Please, if something is not clear, let me know. Is everything still okay?
Yes.
Okay, good. So now, the comment is that, like I mentioned, stress and strain have the same order. Both are second-order tensors. So which means that it can be described by matrix 3-3. So whatever applied to the stress tensors, also the same to the strain tensors. Okay, so go back to the previous slide. If we want to get the principal stress, then we simply solve these equations and we got the principal stress. All right, so this is the same as what you learned in mechanics of materials when you need to determine the principal stress or principal strain. But what you learn in mechanics of materials is with the long equations for plane problems, only involving planar situations. Here, this equation is compact and it can be used for 3-dimensional situations. Okay, so what you learn in solid mechanics is for 2-dimensional case. Here, we use it for 3-dimensional situations. Okay, so let's have a look on this simple example for 10 minutes. Take a piece of paper. Okay, let's stop for 10 minutes. Now is 12:12. So please submit it before 12:22 in Spectrum. I will open the submission link in Spectrum. As usual, like last week, take a piece of paper, write your answer in a piece of paper. Then you can either scan it or snap a photo and then upload it into Spectrum. So I will open the submission link for this example number 6. Okay, so here is the questions. You have the matrix of the strain, okay, which is 0, gamma, 0, gamma, 0, 0, 0, 0, epsilon ZZ. Again, we are working using symbol, not number. Okay, it's okay. So gamma, gamma, epsilon ZZ. The rest are 0. Okay. So you need to find what are the 3 principal strain. Obviously, from here we have components of shear. So these are not the principal strain. Okay, these are just the normal component of the strain. Happens to be 0 here, 0 here, epsilon ZZ here. And then you have shear component gamma here equal to this one, symmetrical. Find the principal strain, lambda 1, lambda 2, lambda 3. Okay, how we do that? By solving these equations. Determinants of this matrix equal to 0. So you can replace epsilon xx by 0, minus lambda, so it becomes minus lambda, epsilon xy by gamma, and this one 0, this one gamma, this is minus lambda, this is so on and so forth. So you insert the value of epsilon component here, get the matrix, get determinants equal to 0, make it equal to 0. You will have polynomial order 3, solve it to get the 3 roots, which correspond to the principal strain that you need. Okay, so 10 minutes from now, again, well, 12:14. Let's submit by 12:24. I will be back at 12:24 to discuss about it. Okay, please make sure you submit. So I have opened the submission link, submission for answer to example 6. Okay, so I've seen that only 6 of you managed to submit. Okay. So let's have a look on how to answer these questions. So here we need to find the principal value of the strain. Okay, so the tensors of the strains is given there. So you simply need to solve determinants of these terms equal to 0. Okay. So how to do that? So this is our tensor epsilon, the strain tensor. All components are 0 except here in the plane xy, the value is gamma, and then on the z there is normal strain along z component. Okay. So what we need to do, as I mentioned, is that we simply need to solve these equations. Determinants of epsilon minus lambda I equal to 0, which means that I have to solve this equal to 0. I need to get the determinants of the matrix inside there equal to 0. So when I do that, I have these equations. So as you can see, this is polynomial order 3. So epsilon zz minus lambda, lambda square minus gamma square. Polynomial order 3 on lambda. So lambda is the variable, the unknown. So we have to find the three roots from these equations. So obviously you can see here that this polynomial order 3 on lambda here equal to 0 if the first term here is 0 or the second term here is 0. So you can see immediately the three roots that we need. There is a question from Andre, gamma is just a pure number. Yes, gamma is a number, but I do not put number, I just put on a symbol. That's what I mentioned. Okay, so I want you to get used to work on symbol, not on number. You can always insert the numbers later, but I want you to get use mathematical operations using a symbol. Okay, so gamma is a number, epsilon zz is also a number, the rest 0. Okay, all right, so immediately from here you can easily get that the first lambda is epsilon zz. So one of the principal strain is epsilon zz. What about the second and the third? Is solving this one equal to 0. So what we have is simply this one. So the three roots are gamma, minus gamma, and epsilon zz. Okay, so these are the three principal strains. Which one is number 1, which one is number 2, which one is number 3, it is not important. Okay, you are free to decide which one you want to call principal strain number 1, principal strain number 2, and principal strain number 3. Doesn't matter. Okay, the most important thing is that once you have decided which one is number 1, which one number 2, and which one number 3, later on you need to determine the principal directions. So you will see in tutorial what is how to determine the principal directions. So there will be principal directions belong to lambda 1. There will be principal directions belong to lambda 2. There will be principal directions belong to lambda 3. So first you need to decide from the principal value of the strain which one is number 1, number 2, and number 3. It's up to you. But once you have decided, you stick with it. Which one is number 1, which one is number 2, which one is number 3. For me, number 1, I choose gamma. Number 2, minus gamma. Number 3 is epsilon zz. Later in the tutorial, you will learn how to get the principal directions belong to lambda 1. The principal directions associated with lambda 1. This is how we call it in the text. We will also determine what is the principal directions associated or belong to lambda 2, belong to lambda 3. Okay, so from this is that if I express tensor epsilon with respect to x, y, z in this way, if I express with respect to the three principal direction n1, n2, and n3, so I put in this way number 1, number 2, number 3. How if I choose different way of numbering? It's fine. Let's say I put here minus gamma, this is epsilon zz. It's fine. no issue. The most important thing is that you know what are the three principal strain. And later on, you will check what is N1, N2, and N3. So it is a pair, it is a couple. N1 belong to lambda 1, N2 belong to lambda 2, N3 belong to lambda 3. All right? Is there any question so far? Is that clear?
Yes.
Okay. So now, as you can see, if you express with respect to the principal direction, there are no shear components. Okay. So what does it mean physically? Here, for instance, you have a rectangular here with respect to, let's say that it is at the plane to make it easier to imagine. This is axis X, this is axis Y. So I can get this square from black line here to become red line here, the deformed state, if I apply shear along the side here in this way. Okay, and when we do that, the strain state is described by this matrix with respect to X and Y. So I have strain on the plane XY, which is here and here. Okay, this will be equal to saying that I can also get the red shape from the black shape here by using other coordinate system. For instance, this is N2, this is N1, but instead of applying shear, I apply tensile along N1 by the amount of gamma. And then at the same time, I apply compression by the amount of minus gamma along these second directions. So this is the meaning of changing from a normal basis to the principal directions. So you can here get the deformed shape by applying shear, or you can get the same deformed shape by applying tensile along the principal directions and compressions along the second principal directions. So this is the physical significance of what we did. So the deformed state is exactly the same. So we are describing exactly the shear, the deformations of the materials by epsilon. How we do that? Either we express in this way, which physically means is applying shearing, or the second way here, which physically means that we simply pull in one principal direction and push in another principal directions. That's the physical meaning. Okay. No questions so far? Okay. If no questions now, so what you will learn next is how that we specify the components of the stress. If I have cube elements, what will be the correct names for the components? For instance, let me just simply zoom it so that you can see clearly. Okay, here you go. Here, if you look at this plan, then the normal stress is here. This is along y-axis. Then it is easy to understand why the name is sigma y or sigma yy. In my case, I always call twice. This plan, the normal stress is along z-axis. That is why it is easy to understand the name is sigma z or sigma zz. Similarly, here in the third plan, it is easy to understand why the normal stress is called sigma x or sigma xx, simply because it is normal stress along direction x. The next question is, how about the shear stresses here? Why this shear stress is called tau yz? Why this shear stress is called tau yx? Because if you replace this with number, then refer to the matrix of the stress, then you need to put it in the correct place. If you do not specify the correct index here, you will not be able to put the components in the correct place in the matrix. Why the shear stress is tau zy? Why the shear stress is tau zx? So here, the next is that we will learn how to specify the component of the stress with respect to certain plane. Okay, so the regulation is very simple. Let's say if I have sigma ij, the index is ij, so I refer to the normal of the plane on which the stress act, which means that look at the plane. What is the normal directions of the plane? Normal means perpendicular to that plane. J refer to directions of the stress itself, in which direction the stress is. So two things, again, you have to remember: the normal of the plane and the directions of the stress, I, J. What if I forgot which one come first? Doesn't matter. You can also change this become J, I, doesn't matter. The most important thing is that one index corresponds to the normal to the plane, means that the direction perpendicular to the plane in which the stress act. The second index corresponds to the directions of the stress itself. Okay, so with this in mind, now have a look here, the constructions of the stress tensor with respect to two coordinate systems that we will use, either, for instance, Cartesian coordinate systems or cylindrical coordinate system. Here, you see that maybe it is easier here. Oh, never mind. It is also fine here. So if I look at this one, can I zoom this? Is it easy? Okay, yes. Let me zoom this one. Okay, so for you to easier to understand. Why this is zy, why this is zx? For this one, it is straightforward. It is normal stress along z-axis, so it is sigma zz. So if sigma zz is 10, you put 10 here in the place of sigma zz. But here, where should I put if it is shear stress? Because we don't know. We use the principle that I explained before. Okay, so why it is zy? Because first, we look at the first index, we look at the plane. The plane is this one. What is the normal? The direction perpendicular to this plane? It is z direction. That is why it is put as z. In which direction the shear stress is? It is along y. That is why it is zy. Can I change it become yz? Yes, you can, because it is symmetrical. So if, for instance, tau zy is equal to 5 megapascal, then the 5 megapascal, you need to put it here and here. Remember, it is symmetrical, the shear stress. Okay. Similarly here, why is it called zx? Because we look at the plane, the normal of the plane is along z-axis, and then the shear stress itself is oriented along x-axis. So it is zx, tau zx equal to tau xz. If tau zx or tau xz is equal to 1 megapascal, then I need to put it here 1 megapascal. At the same time, here also 1 megapascal. I hope that is clear. Yeah, how we put index. So similar things goes also if we use cylindrical coordinate system. In cylindrical coordinate system, we have axis instead of x, y, z. It is radial directions. If we imagine a cylinder, direction radial is the directions from the axis of the cylinder outward. Okay, so this is the radial directions. You can have tangential directions theta, all right, perpendicular to the radial directions. Okay, and then the third one is the z-axis, which is the axial axis or the longitudinal axis, which is the axis of the cylinder itself. So in this way, you can do also the same thing. If, let's say, if I zoom it here, so here I look at the plane on the top. Here, the normal stress is obviously sigma zzy because it is along direction z. The normal stress here in this plane is long direction theta because it is axis theta. Okay, and then the normal stress here, it is sigma rr because it is along radial directions. If I look at the top plane here, the shear stress here is called zr. Why it is called zr? Because if I look at the plane, the normal of this plane is along z directions. And why is it r? Because this is the directions, r directions. This is z theta. Why is it z theta? Because the normal of the plane is z, and this direction is directions theta. So if I have tau z theta or tau theta z equal to 10 megapascal, then this tau theta z, I need to put it here 10 megapascal and also here 10 megapascal. This is how to put it properly. Okay. So let's have a look directly to this last example for today. Or if I have time, then I will just simply finish it all. Yeah. So the question is, construct the stress tensor in the cube element below subjective to the following stress state. So here I have a cube element. The axis that I use is this one. So when you need to construct the stress tensor, what does it mean? You need to write it, the stress state, in the form of matrix 3-3 with respect to x, y, z coordinate system. So there are stresses green here. Obviously, is normal stress, 10 megapascal. You have another normal stress here in red color, 12 megapascal. And then you have some shear stresses. So the black one here, 4 megapascal. And then here, the yellow one is 6 megapascal. So what happened is that if you look at normal stress, they come in a pair, 2 arrow. Normal stress, up, down, left, right, to maintain equilibrium. When it comes to shear stress, there will be 4 arrow. Okay, so here in this plane, second plane, below plane, and on the left plane here, there will be 4 to maintain equilibrium. Okay, so the question is how to write in the matrix. Okay, so just quickly, few minutes, what do you think the matrix will be? So obviously, for the normal component, it is easy. I have here normal stress 10 megapascal along z-axis and normal stress along y-axis. So if I write it in the form of matrix, then it will be this one, the normal part. I don't have normal stress along x, so it is 0. I have normal stress along y, so it is 12 here. And I have another normal stress along z, 10 megapascal, so I put it here. Now, I have 2 shear stress, which is 6 and 4. Where should I put this 6 and 4? And then to help you, you can look back on how we define the index of the shear stress. So I need answer, feedback. Please write it in the chat. So 4 megapascal, in which plane is it? Is it XY? Is it XZ? Is it YZ? Which one?
YZ, 4 megapascal should be a YZ or ZY.
YZ for that one, okay. And then for 6 megapascal?
Be XY or YX.
Okay. Good. Okay. So no. Okay. Nurul Atira and Hadif, XY is for which one? For 4 or for 6? For 6. Okay. Same answer as before. Hadi, right? Who answered just now? Okay. Good. So for shear stress, very well. So this one, the yellow one is correct on XY plane. Okay. And then for 4, it is on here, which is ZY or YZ. Okay, ZY or YZ here. So it has to be come in a pair, right? So in total, this is the final stress tensor. So this is how we represent this stress state in these elements in the form of stress tensor. All right. Any questions so far? Okay, no question. So it is clear, yeah? So you just simply refer to what is the normal of the plan, and what is the directions of the stress itself. Right. I will go to the last example quickly, the last one, the end of this lecture. So this is the problems that you have learned in mechanics of materials, cylinder under torque, under torsions. And then we have learned that cylinder under torsion will generate shear stress. Remember? So what is the amount of shear stress? You have learned the equations that the shear stress, for instance, is tau equal to the amount of torque, T, times the radius at which we want to evaluate the shear stress over the J, which is the polar moments of inertia of the cross section. Okay, so that's how we calculate it. Tau, the shear stress, TR over J. You have learned that, you can calculate that. If you know the amount of torque, you know what is the radius, you know the cross sections, you can get the J, you can get the R, you know the value of T, you can calculate this, the shear stress. And you have learned that the maximum shear stress is on the surface, the outer surface. My questions now is that if I want to describe the stress state in a point M located in the surface, the shear stress that you calculated in mechanics of materials, if I want to put it in the form of matrix, where should I put it? That's the next questions actually. Construct the stress tensor at the point M located at the surface of the solid circular shaft used to transfer torque T from a turbine to a generator. Use the cylindrical coordinate systems. Because it is a cylinder, it is easier to use R, theta, Z. So write down your matrix, something similar like this, except that it is no longer with respect to X, Y, Z, but it is with respect to R, theta, Z. Okay, R, theta, Z here. And we know that under the torque, it will generate shear stress. So my question is, where should I put this shear stress? What do you think? In which plane? Is it in the plane R theta? Is it in the plane RZ? Is it in the plane theta Z? So to help you, let's have a look here. You have learned in mechanics of materials, free body diagrams. Let's say that you have torque here in equilibriums. And then if you imagine that you have line here initially like this, and then when you twist it, then the line will be twisted. And then if I cut somewhere in the middle here, then you can have distributed internal shear force there. Okay, and then this internal shear force will generate shear stress, okay, in the cylinder. So let's say that if I take one element on the surface, so the shear stress will act in this side, which is this one. Since it has to be in equilibrium, then all side there will be having shear stress. And let's say that this is the axis of the cylinder, which is Z-axis. So now, what is this stress? Is it tau R theta? Is it tau RZ? Or is it tau theta Z? What do you think? Please share your opinion in the chat box. Yeah. Where do you think I should put the shear stress because of torque? Is it along R theta plane? Is it along RZ or is it along theta Z? Any idea? How to answer this? So the shear stress will act. I need probably to zoom it also. All right, here we go. It's easier. I hope you can see clearly. This is the plane, okay, on the top. This is the surface, the outer surface of the cylinder. And this is the inner part. This is the one surface, second surface. So this is in the first surface, the shear stress act there. In the second surface here, the shear stress act there. Okay, so there are four here. Okay, and then it is one shear stress. How to know? Okay, you can choose, up to you which plan you would like to consider, because it will give you the same answer. You can look at this plan on which the shear stress act, this plan, or another plan behind, or another plan here on the side. Let's, for instance, have a look on this plan. Okay, on the right here. What is the normal of this plan? Z. So one of the index must be Z. In which direction is this stress? It is along tangential direction. So another index must be theta. So the tau will be tau theta Z, which is equal to tau Z theta. That's the answer. How if I use this plan? Doesn't matter. What is the normal of this plan? Theta. What is the directions of this shear stress? Z. You come back to theta Z. So which means that the shear stress act there is tau theta Z or tau Z theta. So the matrix that you have is 0 everywhere except on this one, the value of shear stress, where tau theta Z or tau Z theta equal to torque times R over J, and then this is the J for the hollow cylinder. So what you learned in mechanics of materials, we never ask questions when it is put in matrix in which plan it is. Here it becomes clear in which plan that this shear stress act. It is on the plan of theta Z. So I think with that, I have finished vectors and tensors, stress and strain tensors. Okay, it's almost one. So if you have any questions, quickly, probably there are things not clear yet. Questions?
Clear.
Okay, good. No other questions? All right. So very well. So whatever I have recall here will be used in the next lecture. So please make sure that you understand it well. Have a look back on the lecture note. So next week we have another class going to the second lecture, which will deal with, let me check, okay, the mechanical behavior of materials. So I have made a review on the stress and strain. So I will discuss next week on various mechanical behaviors that you can encounter in the materials. Okay. Again, if you don't have any questions, I will see you next week. Yeah. If you have other questions, you can always email me. All right. See you next week. Bye.
Bye. Thank you, Doctor.
Thank you, Doctor.
Okay.
Thank you, Doctor.